Welcome to Module 4, Creating Soil and Changing the Atmosphere of the workshop Deep Time Paleobotany and Plant Evolution. Plants moved onto land quite a long time ago. Initially, they were growing close to water. Gradually, they developed roots and eventually seeds. And all these things made it possible for them to move further and further away from water. They started to root deeper, and that had an incredible effect on the landscape. So what I'm going to talk about now is a little bit about paleobotany, but also how they changed our planet, and especially creating the soil, and by photosynthesizing a lot, how they changed the atmosphere so much that we ended up in an ice age. So the time period that we're looking at is the Devonian, that is part of the Paleozoic, and it's roughly 416 to 359 million years ago that this module will cover. Plants moved onto land roughly 470 million years ago, and that is not indicated on this diagram because initially, if you look at the left, around 440 million years ago, we don't really know what the plants looked like. Likely they were bryophyte-like, so they were more or less substrate-hugging ground cover. They did not have roots, so they would not go, there was nothing going into the soil. So going from the left to the right, we're going from older to younger. Cooksonia was the first land plant that was discovered that was relatively complete. Other plants getting bigger and bigger through the Devonian. On the right, you see the maximum height. This is 6 meters. There is a break here. These plants completely on the left got even bigger. But you can see that they go from the roughly 3 feet high ones over here to the Eospermatopterus gilboa tree that we talked about, that had a weird looking base. Here they don't know yet what the canopy looks like. Nowadays we actually do. 2 big lycopods, gymnosperms like Archaeopteris, 2 even bigger ones. If we look underground, you can see the rooting depth. And initially there were no roots, so they weren't going very deep in the undergrounds. And gradually, first lycopods have roots, other plants catch up as well, and roots go deeper and deeper and deeper into the ground. And this diagram ends roughly where the Carboniferous begins. So by evolving roots and later seeds, plants become increasingly independent on humid, moist environments. So in the beginning, the early plants were mainly fringing water bodies, and the other areas of the landscape weren't that populated yet. Evolving roots and seeds made it possible to colonize those drier environments. And these are just 3 diagrams that show how the landscape changed. Initially, you had relatively small statured plants fringing water bodies. By the mid-Devonian, plants were getting bigger, still living in relatively moist environments. But by the late Devonian, they could root relatively deep, and therefore also in further away from those water bodies. So the planet became a lot greener. So why is that important? Well, it has a lot effect on the soils, this evolution of roots. And it changes the weathering regimes. So weathering breaks down rocks. It loosens the surface minerals of rocks so that they can be transported away via water or wind or ice. And there are two different types of weathering. One of them is mechanical weathering. And I'm just going to give you an example. An example of mechanical weathering is, for instance, that water, if you have a rock and there is a crack in it, water seeps into those cracks, then it could be that it will freeze. If water freezes, it becomes, the volume becomes bigger and it expands. And it could be that it actually cracks open this rock. That's what's happening here. And when that happens over and over and over, gradually rocks will be broken into pieces. But that's very different than chemical weathering. So chemical weathering actually does not make the rock smaller and smaller and smaller. It changes the original material. So the composition of the different particles. And I'm going to throw in a reaction, and it's not very important that you understand completely what's happening, but I'm going to just talk you through it. Let's weather this silicate rock. So you have a silicate rock, a silicate mineral rock. If you add carbonic acid, and carbonic acid is just CO2 dissolved in water, so water that's slightly acidic, it can react into ions, in this case calcium 2 plus, a bicarbonate ion, and silicium oxide and water. Now the most important thing is this bicarbonate ion it dissolves in water and can be transported through the groundwaters to rivers and ocean. What I haven't told you yet is that this is very interesting. It's CO2 that reacts with water that forms the carbonic acid, and that the CO2 part in the left of the equation so becomes something, an ion that dissolves in water and can be transported into the ocean. That means that CO2 from the air actually disappears from the air. So if you chemically weather silicate rock, you, what we call, withdraw CO2 from the air. And plants increase chemical weathering on the landscape a lot in different ways. So they produce acids with their roots that break, that chemically weather rocks. They produce organic material. If leaves fall on the ground or axes fall on the ground, they start to rot. They produce acids that can break down rocks. So this is happening quite a bit. And you can imagine if you go from a planet where there were no plants on the surface to a planet where a lot of plants are on the surface and roots go deeper and deeper and deeper into the ground, that a lot of CO2 disappears from the air. So this is a very simple diagram, but I still always love it because it just makes things relatively clear. If these little tiny dots that you see in a diagram that represents before plants moved onto land or before the Devonian, you have a lot of CO2 or carbon in the atmosphere. There is not a lot of dirt or soil yet because plants don't, there are not a lot of plants on the surface yet, or there's not a lot of rooting. So therefore the soil layers are not very, very thick. It's just a very flimsy layer. So there's very little carbon actually stored in the soils. So CO2 levels were high before the Devonian. Organic carbon, biomass, and in the soil is relatively low. Then by the late Devonian, a lot of the CO2 that was in the air was taken up to build the bodies of the plants, including their roots, so stored in biomass, but also dead organic material ends up in the soils. Now, what I mentioned before, a lot of the rotting plant matter will rot and will turn into CO2 again. But if you only store a little fraction of what a plant produces in the soil and wait for millions of years, it will pile up. So as a result, CO2 levels in the atmosphere gradually became lower and lower and lower, and organic carbon stored in the biomass in the trees and in the soil becomes higher. We call this time interval the birth of dirt. So then there are other things happening. So before the Devonian, if you would have a river, it would rapidly mechanically weather the sediments that it flows over, and the rivers would produce a lot of sediment that would flush into the seas. And the rivers would be braided rivers. Their stream banks are not being kept in place by anything. By the late Devonian, plants do keep the stream banks in check, and if you see rivers, they were likely more meandering, so more gradual, changing their course, and less sediment would be transported to the ocean. So where you had little, very thin soils before the Devonian, by the late Devonian, the soil layers were relatively thick. So in the late Devonian, you had less mechanical weathering, more chemical weathering, and that means active removal of CO2 from the atmosphere. The volume for chemical weathering within the soils increases because the trees root deeper and deeper and deeper. There was an increase in storage of organic carbon in the soils, and there is increased stream bank stabilization. So I haven't talked about that there are also scientists who actually specialized in studying fossil soils. And here we have a timeline again going from 600 million years ago up to the present. We know roughly when plants moved onto land. That was 470 million years ago. And before the end of the Devonian, you do recognize certain what we call soil types, or paleosols, so fossil soils. But a lot of those soils do not have evidence for life in them. We call them, so these not living or soils that do not indicate that life was needed to produce them are in blue. So by the mid to end of the Devonian, we see different soil types appears. And one of them over here, at the top, is called a histosoil. So the ones that indicate that life was present on the horizon are in green. Now, just a quick example of what you should think about when you think about a paleosoil. Here, a vertisol, so that's one of those upper ones, is a soil that forms deep cracks in drier seasons. Probably everybody has seen these before. So this just happens with clay if it dries out. No plant needed to produce this. The other one is a histosoil, and going back, a histosoil is a very, very organic rich, peat-like soil. So organic rich, it has to be plants that this matter organic part of the soil came from. So therefore we know that plants were there. So going from the Devonian into the Carboniferous, the next period, we see all kind of soil types appear that indicate that plants were already present. And as you can see, the histosoil is very organic rich. So that's also evidence that a lot of organic biomass was stored in these soils. So you probably heard that if CO2 levels increase in the atmosphere, that our planet will warm up because CO2 is a greenhouse gas. The opposite is true as well. If you remove CO2 from the atmosphere, the temperature on our planet will drop. So this is the estimated global temperature over the last 500 million years, and this is a diagram adapted from Smithsonian Institution. And to the right is today, and back to the left is 500 million years ago. And the red and blue lines indicate the average global temperature on our planet in Fahrenheit. So not going into detail with all the wiggly lines, what you can see is the time interval that we talked about in this module is in this gray box. And you can see that initially the planet was relatively warm. So 470 million years ago is when we see first evidence of land plants. And the second arrow shows when the start of the radiation of plants really takes place during the Devonian. And reconstructions of temperatures and CO2 levels indicate CO2 levels are indeed going down, and our planet's temperatures are going down as well, relatively rapidly. They go down so fast, or well, geologically speaking, fast, and it gets so cold that we end up in an ice age. And that's indicated with those blue lines over here. If you go all the way to the right, you can see that we're currently also in a ice house period, but we're slowly moving out of that because the planet is warming up. And one of the things that I'm very interested in my own research is what happens when at the end of the Carboniferous, when the planet starts to warm up again. What happens with the different biozones of vegetation on our planet? But we're not there yet. First, this is what we talked about, the initial cooling, ending up plants changing, chilling out the earth, and creating an ice age. So the effect of vegetation, they stabilize land surfaces, allowing more time for weathering, surface of rocks, more mature fine-grained sediments, paleosols, appear on the landscape. We see profound changes in soil type, thickness, and geographic extents of where those soils are. CO2 levels drop and Earth starts to cool down. And this also opened up niches for exploitation for other organisms. So the take-home points from Module 4 are: roots help plants to migrate away from open water or close to open water. They started to create soil and deep soil for the first time. So roots changed how rivers flow and how much sediment ended up in the sea. Plants removed CO2 from the atmosphere by chemical weathering, and I think there's something missing, and increased the carbon contact in the soil. So this is the end of Module 4, and I'm available taking questions.